Section: Introduction. In this section, we address the challenge of creating 3D worlds from text descriptions. Producing 3D content, such as for video games or virtual reality, is often tedious and time-consuming. Much of the content generated lacks artistic value, and the manual effort involved can be seen as a waste of resources. Generative models can alleviate this burden by automating many of these repetitive tasks. The rise of modern generative AI has greatly influenced 3D content creation, promising to lower production costs significantly. Dream Fusion was one of the first to adapt advanced 2D image generators to create 3D objects. Since then, the field has advanced by refining these generators to produce multiple consistent views of an object and developing networks for 3D reconstruction from few views. Recently, the focus has shifted to learning a 3D latent space, which allows for the generation of 3D objects with more accurate geometry, as this space encodes the 3D structure rather than just the 2D appearance. However, most 3D generative methods have primarily focused on creating individual objects. The most promising application of 3D generative AI lies in building entire virtual worlds, where automation can have the greatest impact. There is considerable research on generating 3D scenes from text or image prompts, with many methods relying on images to progressively reconstruct larger areas of a scene. These approaches combine depth prediction and 3D reconstruction techniques, leveraging powerful 2D image generators to create initial and subsequent views. While these methods can interpret complex text prompts and produce visually appealing 3D scenes, they struggle to maintain a coherent 3D structure across larger areas. For instance, even advanced implementations like those from World Labs can only allow limited navigation within a scene. Extending these scenes beyond small areas is challenging, as image-based methods often lose consistency over larger distances. We believe that 3D generative models may be more effective, as they can better regulate the geometry and create shapes and textures in areas not directly visible. Previous works, such as block diffusion and LT3SD, demonstrate that large, coherent spaces can be generated, but these methods often lack quality and diversity in the scenes produced. Unlike view-based methods, they do not utilize an image generator, missing out on the artistic quality and complex text interpretation that comes from training 2D generators on vast datasets. In our work, we aim to enhance 3D generative models while leveraging the strengths of 2D image generators to create expansive, high-quality 3D spaces that allow for free navigation. We note that while models like Trellis are designed for object-level reconstruction, they can also create complex local compositions. Drawing inspiration from video game world building, we demonstrate that Trellis can generate tiles representing local regions of a world. We specifically show how to prompt the model with an isometric view to create these tiles in 3D. With this foundational capability, we tackle the challenge of generating larger scenes by stitching together multiple tiles. We build on a text-to-image generator, Flux, and introduce a new prompting method that stabilizes the generation of tiles with consistent isometric framing. This approach helps ensure that the tiles fit together seamlessly. To achieve this, we propose two strategies. First, we use previously generated tiles to provide context for the image generator, ensuring visual consistency. Second, we blend the 3D representations of neighboring tiles to maintain geometric coherence. Section Summary. In this section, we explore the generation of 3D worlds from textual descriptions, highlighting the potential of generative models to automate the labor-intensive process of 3D content creation. We propose a method that combines 3D generative models with 2D image generators to create coherent, high-quality 3D scenes by generating and stitching together tiles, ensuring both visual and geometric consistency across the generated environment. Section: Related work. In this section, we discuss related work in 3D scene generation. Rather than just creating images or extending scenes in 2D, some methods generate the scene representation directly. For instance, Set the Scene enhances NeRF scenes by using object proxies to control layout. Block Fusion learns to progressively diffuse small blocks to expand a mesh, using a 2D layout to guide the generation of various scenes like rooms, villages, and cities. However, this method is limited by its reliance on specific 3D training data and produces untextured meshes. LT3SD, on the other hand, employs a diffusion model to create 3D environments in a patch-by-patch manner, but it is restricted to indoor scenes. Meanwhile, advancements in text-to-3D and image-to-3D generation have enabled the creation of complex, high-quality objects. These models, trained on extensive 3D datasets like Objaverse XL, can generate a wide range of objects. However, to our knowledge, no previous work has utilized object generators for scene creation. Our objective is to generate a 3D world from an initial text prompt. We demonstrate how we can use prompt engineering alongside existing language, 2D, and 3D generators to automatically create the entire world without retraining the models. We organize the world as a grid of square tiles, each capable of containing multiple complex 3D objects and the ground surface. We generate the world progressively, tile by tile. When we generate a specific tile, the tiles that come before it in the grid have already been created. Our approach involves several steps. First, we expand the initial world description into specific prompts for each tile. Next, we use these prompts to guide a 2D image generator to create an isometric view of each tile, considering the already generated parts of the world. Then, we extract image prompts from these views to feed into an image-to-3D generator, which reconstructs the geometry and appearance of each tile in 3D. Finally, we align and blend these 3D reconstructions to form a cohesive 3D world. For prompting the language model, we take a high-level description of the world and break it down into specific prompts for each tile, along with a general style prompt. We can create these prompts manually for precise control or generate them using a large language model like ChatGPT from a seed prompt. In the next step, we use the language prompts to guide a 2D image generator to produce images of each tile. These images must meet several criteria. They should reflect the specific instructions for each tile, be suitable for the next step of 3D generation, and remain consistent with previously generated tiles. Our strategy ensures these constraints are met, drawing samples from the 2D generator based on a combined prompt of tile-specific and world-level descriptions, along with a base image and an in-painting mask to guide the output. Section Summary. In this section, we discuss various methods for 3D scene generation, highlighting our approach that utilizes prompt engineering with existing 2D and 3D generators to create a coherent 3D world from a textual description. Our method involves generating tile-specific prompts, creating 2D images for each tile, and then reconstructing their 3D geometry, all without the need for retraining models. Section Main. In this section, we take the context into account. For tiles other than the first one at the coordinates 0, 0, we generate them based on the already created world. To do this, for tiles where both x and y are greater than 0, we adjust the base image and the mask. The base image shows the part of the 3D world that has been generated so far, giving context to our in-painting network. We also change the mask to avoid covering tiles that have already been created to the left. To maintain a continuous ground, we trim any 3D geometry that is too high and could block the tile we want to generate. We also discuss a special case for tiles at the edges of the world in the appendix. Next, we focus on prompting the 3D generator. We start with the tile image obtained from the 2D image generator and aim to create a corresponding 3D reconstruction using an image-to-3D model. We choose Trellis for its strong performance in generating both shape and texture, and its latent space structure, which is easy for us to manipulate later. Thus, generating the 3D reconstruction involves sampling from the image-to-3D generator using a pre-processed version of the image. Moving on to 3D post-processing, we have confirmed the 3D reconstruction as a mix of 3D Gaussians. However, the actual size, orientation, and footprint of the tile are inconsistent. In this step, we refine the 3D Gaussian representation by cropping out the added base, resizing the tile to a standard size, and reorienting it to match the 2D image prompt. Now, we have reconstructed all the 3D tiles. Thanks to the prompting and post-processing steps, these tiles are roughly aligned and oriented correctly, with their ground levels at similar heights in 3D space. Since the 3D reconstructions are represented as 3D Gaussian splats, we can combine them to form the entire world. However, the edges of the tiles may not align perfectly due to the nature of trellis and the single view provided for each tile. Therefore, we propose a method to enhance the blending of tiles, ensuring a coherent and continuous 3D world. Specifically, we regenerate the boundary areas of two adjacent tiles in the latent space of trellis, effectively blending them before decoding into 3D Gaussian splats. Finally, we address upsampling the latents. After rebasing, the 3D reconstruction contains a base, which we have removed in the 3D Gaussian splat space, but not yet in the latent space. We apply the same cuts used in the 3D Gaussian splat space to crop the latents, adjusting for the discrete nature of the latent voxel grid. Initially, we assumed that the latents had the same spatial resolution, but after cropping, this may no longer hold true if the cuts of neighboring tiles differ. Therefore, we need to upsample the cropped latents back to the original grid resolution. We found that simply upsampling through interpolation results in poor reconstructions due to the sparse structure of the latents. To improve this, we first upsample the cropped occupancy volume to the original resolution. Then, we denoise a new set of latents on this upsampled volume, rendering from multiple views to preserve details and textures. We compute the denoising step as the average across all views, leading to better reconstructions. Section Summary. In this section, we describe our approach to generating and refining 3D tiles by incorporating context from previously generated tiles, using a robust 3D generator called Trellis, and applying post-processing techniques to ensure consistency in size and orientation. We also detail our method for blending adjacent tiles and improving the quality of 3D reconstructions through a novel upsampling scheme that enhances detail and texture preservation. Section Main. In this section, we evaluate human preference for the results produced by our method compared to those from block fusion. We specifically look at a city scene, including both the full scene and close-up details. Our findings, as shown in the results table, indicate that participants, numbering 22, generally prefer our method due to its superior geometry, realism, and diversity. Next, we conduct ablation studies to assess the significance of various components in our approach, demonstrating how each contributes to the overall effectiveness. We also explore 3D blending. In our blending figure, we illustrate a scene without applying 3D blending, which leads to noticeable gaps between tiles. For qualitative results, we showcase example scenes generated by our method in another figure, along with detailed views that emphasize the quality and variety of the scenes. Additional examples can be found in the supplementary material. Finally, we sample trajectories to explore the generated 3D worlds, enhanced by a skybox for visual appeal. Unlike trajectories from world video models, ours maintain consistency and avoid semantic drift. Our method also creates navigable spaces that are significantly larger than those produced by other systems that only generate limited environments.